Hello everyone, welcome back to the KM32003 Finite Element Methods class. Today we will go through the third chapter related to the prismatic bar. Prismatic bar actually is infinite elements itself. Okay, so previous week or previous lessons we have gone through the derivations for a spring element. In the spring element itself, we don't really use it in the finite element analysis. Okay, but then it serves as a purpose to reinstate the relationships behind or the concept behind the finite element methods. Okay, so today we will go into the first finite elements, okay, which is the prismatic bar, and these chapters will relates to applying the knowledge of the mathematics, science and engineering. Okay, then from there we will again set the boundary conditions and the problem inertials, right, by discretizing our models, right, and finally we solve them. Okay, so this prismatic bar would be a finite element which is used to solve structural problem. Okay, all right, so look, as we have seen previously, again, as to mention this, that this materials, okay, for these slides are mainly derived from the books Logans, right? The books are written by Professor Logans. Okay, all right, so as we have seen previously in the Lisa finite element analysis software, okay, the first thing when we start to draw, you have to select the elements, right? There are a lot of elements, and you can see that the first elements that you can see there is the beam or the truss type of element, and that is where it is related to the bar element, right? It's related to the bar element, which involve only two nodes. Okay, line, a straight line with two nodes. Okay, so we have node number 1 and node number 2. Okay, so this is a bar element. Okay, as you can see, we just represent a rectangular shapes, okay, to represent the bar itself, okay, with a length of L with two nodes, and the force T is acting at the node, okay, node number 1 and node number 2. Okay, and it causes certain displacement at node number 1 with U1 as well as U2. At the same time, there might be forces acting at node number 1 as well as node number 2, denoted by F1x and F2x. Okay, so the directions of the movement is along the x directions or along the axis of the bar element. So now, as you can see, this bar is subjected to a tensile force T, okay, as we have seen here, okay, attached to the node 1 and node number 2. At the same time, we made an assumptions that this bar element will have a constant cross-sectional area A, okay, across it. Okay, so we assume they have the same cross-sectional area. Okay, at the same time, we assume the material used here will have the same modulus of elasticity, okay, E, or in other terms we call it as Young modulus, okay, as well as the inertial length, the length of the bar element, right? So you have to imagine that this can be very long or can be very short, okay, that you use it to form your mesh, right? Remember, you have to create or discretize your model into meshes, right? Now, the nodal degree of freedoms are the local axial displacement along the x directions. Okay, so you will have u1 as well as u2, and since we have only two nodes, meaning to say in this bar element there are 2 degrees of freedoms. Okay, so again we will use the Hooke's law, okay, which relates the stress to the strain, okay, by the modulus of elasticity, right? And at the same time we know that the strain is actually the changes in displacement respect to the original length, okay, original length, so du over dx. Okay, for the loads which apply at the ends of the bar, okay, which is the t, we can say, okay, we can denote that as a t, and this t, as we say, is a force, and this force, when we act across a constant cross-sectional area, it gives us the stress, right? So we can derive the stress is equals to the tension divided by the cross-sectional areas. Therefore, we rearrange, we have A stress or A sigma equals to T, and this term should be a constant, right? Since the cross-sectional area is a constant. Alright, so now we will start to resubstitute. Okay, so this one substitute over here, and this sigma we substitute over here, then eventually we get this this term. Alright, and when we differentiate it with respect to x, okay, then since it is a constant, therefore the derivative of it would be equals to 0, and it gives us the so-called linear elastic bar behavior, okay, of the finite element. All right. Okay, so in this derivations of this bar elements stiffness matrix, okay, there are a few assumptions that we have made previously, right? If you have noticed it, okay, as you can see, first thing is the very important one, okay, the rules number 3, or the assumption number 3, we assume Hooke's law is applied. Okay, there are a proportional relationship between the stress and the strain. Okay, then for the other assumptions, it includes that in this bar elements there is only forces along the axial directions, okay, along the x directions. The bar cannot sustain any shear force, okay, meaning to say we don't have a force in the perpendicular directions, okay, that create the shear across the cross-sectional area, right? Or any bending moment. There is no twisting or bending moments, okay, acting on the knot 1 or knot 2, okay. So this bar element that we will use in the finite elements, okay, cannot sustain these two kind of forces, right? Meaning to say, if it is being used at the conditions where it requires or it has so-called shear force or bending moment acting on it, then this bar elements being selected will not be suitable, okay. You will not get the right result as you need, okay, or you cannot solve for the shear force or the bending moment as you need it, right? So you will get different results, okay. So therefore the selections of the finite element is important, okay, depending on the characteristics of the derivations behind the finite element. Okay. Besides that, since we do not, or the bar element itself cannot sustain shear force, okay, or the bending moment, okay, therefore any effect on the transverse displacement is ignored, okay. So we don't actually care or take into considerations any displacement in the transverse directions, okay. And at the last assumption is that, as we have seen previously in the derivations, okay, as well as in the derivations of the spring itself, there are no forces or load actually acting in between the two nodes. Okay, we only put the loads at the node. Okay, there is no intermediate applied load, okay, along the bar, right? So we cannot put any loads, okay, across the position except the nodes itself. Okay, if you would want to apply forces in between, then you have to divide them into two different elements and so on, right? But in the element itself, we cannot put any load. All right, so we just go through again the 7 steps, okay, as we have applied in the spring stiffness or the springs method itself. Okay, yeah, spring stiffness method itself. Okay, so first thing first, we have to select the elements. Okay, so if we select the line tool, okay, in the Lisa FEA software, then basically you are actually selecting this type of element where the previous 4 assumptions that we have described is applied to our derivations. All right, so once we have selected this finite element or this bar element itself, then we have to select or the equations running behind this finite element methods is basically this depending on this displacement function. So in this element itself, there is only 2 degrees of freedom, and as we know, because there is only 2 degrees of freedom, the best approximations displacement functions selected, okay, being selected would be a straight line equations, right? We have a1 plus a2x, okay, and it forms these characteristics, okay, of linear changes across the length of the finite element, right? So you can describe it in this form. Okay, so how you get this into this, they are exactly the same with the spring spring elements. Okay, so this is the recap that we have gone through in the previous lessons, right? So exactly the same displacement functions, right? Therefore, when we derive, you would end up getting this. Okay, and at the same time, if you re-express this into a matrix form, you would again come to the stage where you get the shape functions given by 1 minus x over L and x over L. Okay, remember we have these shape functions. Okay, so as we have seen that the displacement function is the same for the bar as well as for the spring. Therefore, you would expect the same shape functions, okay, for the bar, right? So you would see the exactly same shape functions being derived for this bar element, right? So basically it's the same equations. Okay, so what is the difference is that when we start to derive further, okay, for the spring we just use the relationship of force equals to kx, right? Very straightforward relationship. But then for a bar itself, we need to apply some kind of strength of materials or maybe engineering materials knowledge, okay, where the Hooke's law being applied, and this is the Hooke's law relationships, okay, between the stress and the strain itself. At the same time, we would want to apply such that the stress is equals to the force divided by the cross-sectional area, right? So the same equations that we have derived previously, and when we rearrange this, this minus should be here, sorry, okay, so this minus should be here. So when we rearrange this T equals to A, and this stress, we just substitute this E epsilon over here, and this epsilon is basically u2 minus u1 divided by L. Therefore you will get T equals to A E over L u2 minus u1. right? So you have derive the element stiffness matrix and equations based on the knowledge of the material properties. Okay, so based on that, okay, onwards we will start to define the forces, okay, acting at the node 1 and node 2. So we will have T, okay, acting at the different directions, okay, assuming we apply a tensions on the on the bar element itself. Therefore at node number 1, the nodal force sign would be minus T, okay, on the other side would be T. So since we know the T is equals to this, we just resubstitute into the equations, rearrange them later on into matrix. You will see it in this particular form, okay, and this particular form, again, as you can see, is very similar to what you have seen in the spring element stiffness matrix. Okay, so you have F1x equals to AE over L, 1 minus 1 minus 1 1, okay, U1 or U2, right? So in this form itself, the K, or the prismatic bar stiffness matrix, okay, stiffness matrix will be represented by this particular terms, okay, which contain AE over L. Okay, if we compare these terms with the spring element stiffness matrix, okay, basically this K, now it turns to be AE over L, right? So this functions represents how a prismatic bar will act like a spring, okay, with these K functions, okay, will act like a spring, right? So you can see that the relationship between the force and the displacement is that if we increase the cross-sectional area, or we increase the modulus of elasticity, therefore the force required to change one unit of displacement will increase proportionally, right? So we increase proportionally, whereas if we increase the length of the element, okay, at the denominator sections, therefore it will decrease the so-called prismatic bar stiffness matrix, and at the same time when it decreases, meaning to say the force required would be lower, okay, when we want to make the same kind of one unit of displacement, right? What is the relationship between the AE over L on the stiffness matrix itself? Okay, so as we have discussed in the previous lessons, okay, after we have derived the stiffness matrix, okay, for the local elements, therefore we can start to assemble them into a global matrix, okay, by some superimpose or superpositions all of the stiffness as well as the forces, okay, acting on every single element itself. Okay, then once we get that, we will slowly solve all the simultaneous equations, and once we have solved all the simultaneous equations to get the nodal displacement, then we will we will do a back substitutions of the nodal displacement in order to get back what is the element forces acting at every single element itself. All right, so the methods would exactly the same, or the concept is exactly the same with the spring spring stiffness methods. Okay, so since they are same, so what you would expect is that, remember in the previous lessons we mentioned about the direct stiffness method. Okay, you can use the direct stiffness method to assemble the stiffness matrix, right? Okay, so it would be able to apply over here. Right, so just quickly go through this example 3.1. right? So basically this examples is very similar to what you have gone through in the practice. Okay, if you have try it in the spring. Okay, the only difference is that now this is a bar, okay, instead of the spring form, right? This is a bar instead of the spring form, and this bar itself will contain different parameters. For example, they are modulus of elasticity given, they are cross-sectional areas of the elements given, okay, as well as the length, okay, of the or the initial length of the element itself, right? So this shows a 3-bar assemblage problem, okay, to represent maybe one single bar, okay, but we just break them into or we want to analyze it, okay. So the original problem could be just a simple problem like this, okay, but then when we try to transform this actual physical model into finite element, okay, so we can okay simplify, or we can try to solve it by using 2 nodes, 3 nodes, depending on what you want, right? So you can transform it into 3 nodes, okay. So in this case we intend to solve it using a 3-bar assemblage, right? So this is a 3-bar assemblage examples, right? So remember, don't forget again, there is an assignment, okay, in the lecture 2A, right? Lecture 2A that's require you to run a simple structural analysis, right? So this is how you can do it, right? You just describe as very simple examples, okay, then discretize them into maybe 2-bar, 3-bar, or whatever the numbers of bar that you would like to do, then you just run an analysis on it, right? So now for practices purpose or example purpose, we just use the 3-bar, okay. But when you are using software, you can mesh as many as you like until maybe your computer cannot sustain, or maybe until the time taken for you to solve it, or the memory required to solve it is insufficient. Then yeah, it's up to you, okay, and your computer in that particular sense, okay. But for practice purposes, we just run maybe 2-bar or 3-bar, okay, or 2 elements or 3 elements assemblage, right? So here we use 3 element assemblage, where the first 2 element, okay, again before we start we have to number our element 1 2 3, element 1 2 3, and the numbering of the nodes, okay, we can number it 1 2 3 4, or if you like you can also number it like the previous chapters. You can number it 1 2 3 4, okay, up to you, okay, as long as the numbering is written there. Then after that what you need to do is you just make sure they are consistent, okay, when you form the matrix, okay, the matrix, right? So for the first and the second element, basically they are the same, since they have the same area as well as the so-called modulus of elasticity, okay. Whereas for the element number 3, they have different parameters, okay. So they are the same, therefore we just have AE over L, okay, bracket 1 minus 1 minus 1 1, okay, for the first and the second, okay. Whereas for the third element, the stiffness matrix would be that again AE over L, right, it's given as this, okay. So when you recalculate them, yeah, eventually they get the same number, right? 10 to the power of 6, okay, for each of these, okay. Cancel out this one, 2 times 15, okay, so cancel out, right? So eventually, yeah, just lucky you get the same number, right? But then numbering of the node is important. The first element is node 1 connect to node 2. For second element is node 2 connect to node 3. For third element is node 3 connect to node 4, okay. So numbering is important. So therefore when you assemble it using the direct stiffness method, Okay, so this would be representing 1 2 3 4, 1 2 3 4, right? So 1 2, so 1 2, right? And then 1 2, so this 1 minus 1 minus 1 1 is come from the first element, right? Then for the second element, it's related to number 2 and 3, so these sections, right? So you have a plus 1 minus 1 minus 1 and plus 1 over here, okay? And then for the third element, it's related to this particular part, okay, which is the third and fourth elements as third and fourth row and column. Therefore we have 1 minus 1 minus 1 plus 1, okay? So we have formed the stiffness matrix easily, right? We have assembled it easily, okay, using the direct stiffness method, right? So once we get that, what we need to do next is just to assign the boundary conditions, okay? So in this case, since we have two walls, okay, to fix the positions of node number 1 and number 4, therefore the U4 or D1 and D4 should be equals to 0. D1 and D4 should be equals to 0. And since D1 and D4 equals to 0, therefore this rows as well as column will be turned into 0, okay, when you multiply them. So the effective regions would be this second and third, right? So second and third, so what we need to do is we just partition them out, right? So we just concentrate on the second and third, okay? So we write 2 minus 1 minus 1 2, okay, second and third, so D2 D3, and then second and third we just look back again, second node and third node, okay? Second node there are 3,000 pounds, and the third node no forces acting on it, right? So 3,000 0, right? So based on this matrix, you solve them simultaneously to get the displacement at node number 2 and node number 3. So once you get that, you can continue to solve for the rest of it, right? So the rest is just mathematics, okay? So that is the idea on how you can solve it now using a bar element, okay, instead of the spring element, okay? The only difference is that you have to use the parameter A, E divided by L, right, instead of the spring constant or the spring stiffness, okay? So now we move into basically the displacement functions, okay, or here we say approximations functions for displacement, right? So in short, it's basically the displacement functions that we have derived for the bar element, okay? There are 4 guideline or criteria that you need to take care, okay, or you must keep in mind, okay, when you want to derive for the displacement functions, okay? So by knowing these 4 guidelines, therefore you can actually derive or select the displacement functions, okay, or create your own displacement functions, okay? Create the displacement functions according to your needs, okay? So now we use this concept for the bar elements. Next, you slowly apply it to the other type of elements, okay? So you will see that basically they have to comply to these 4 guidelines, okay? The first one would be they can easily express in terms of shape functions, and one common approximation is that generally they are in the form of polynomial. That's it, okay? The first thing, very straightforward. Generally they are in the form of polynomials, okay? Starting from the simplest one, linear, and then slowly you have more complex functions, right? Next is that that particular functions now, okay, or the polynomials itself must be continuous within the bar itself, okay? So if you draw a line, okay, so this is our displacement functions, okay, that you have known previously. This is a straight line function. So when we draw the displacement across the the elements, you will see that it may increase as the length increase, right? So you have this kind of displacement functions. Okay, it's a straight line. What happens is that you can see that this straight line is continuous. They do not have in the form like this. Okay, if therefore this is a proper one. All right, we don't want a function such that it will create the functions like go straight, okay, then come, okay, to the down, okay, then suddenly jump over there. Okay, this shows discontinuity, okay, in between them, right? Therefore, generally, if we select a functions, okay, a polynomial functions, okay, generally we will generate a continuous line, okay, connecting them together, right? That is why we would want to use the so-called polynomials to describe the displacement functions. All right, so next would be what, or maybe why we need this displacement function, is that we would want to prevent opening, overlapping, or jump, okay, in the displacement. Okay, like this is a direct jump down and jump up, right? Or maybe discontinuations or opening between them, right? So we don't want to have this kind of thing. Okay, when there is go down and go up, meaning to say this point maybe move or maybe go to the negative side, so meaning to say certain point will go backward, certain point go up the other side. It creates an opening or overlapping. Okay, you will create this kind of problem, okay, if the linear functions or the displacement function is not a continuous value, right? Then once we have taken care the functions within the elements, next we would want to check, okay, inter elements. Okay, beside in between elements, we would want to ensure that these connections, okay, where there is a common node here, okay, element number 1 and number 2, they are connected at a common node. Therefore, these common nodes must behave with the same so-called, again, displacement characteristics, right? So therefore, this not due to element number 1, let's say it move 3 mm, okay, and this 3 mm must be equals, okay, on the node number 2, okay, to ensure that they are continuous. Okay, so therefore here the third guidelines that you may need to take care or check is that the common nodes, okay, must remain common. Okay, you don't want it to be due to node number element number 1, the displacement is 3, due to node number 2 at this common node the displacement is 2. They are not matching. Okay, therefore if they are not matching, there is a possibility of overlap or maybe a void, right? So if due to 2 is only 2 mm, okay, due to 3 due to element number 1 is 3 mm, okay, so it causes a gap in between them, okay, and this gap may cause overlap or void between the elements. Okay, so we don't want this to occur, right? So make sure there is continuity between them, right? So based on that concept of continuity, therefore the displacement at node number 2 for element number 1 must be equals or should be equals to the displacement at the same node number 2 for element number 2. Okay, we don't want it to be having different values. Okay, and these linear functions, when they comply to this, we call it as conforming or compatible functions. Okay, so when they comply to these inter elements conditions, okay, these functions we call it as a conforming or compatible functions. Okay, and it would make sure that it satisfies both the continuity between adjacent element, okay, in between two elements, and the continuity within the element, okay, within each of these elements, okay. We call it as conforming and compatible, right? That it would be a good or the proper type of displacement functions, okay. And then finally, the fourth guideline would be the approximation should allows the rigid body displacement and for a state of constant strain within the elements, okay. Meaning to say, for example, in the one-dimensional displacement functions, which given by the a plus a1 plus a2x, okay. So a1 will give the so-called displacement, okay, allow the rigid body to displace, and then there is a component of a2x, okay, which allows the strain, okay, the straining within the elements, okay. So the element itself is allowed to displace freely, okay, plus the element itself is allowed to change length, okay, within the elements, okay, constant strain within the element, right? This is the idea. So once they have complied to this so-called all the guidelines, all right, therefore we would say that the whole elements basically is complete, all right. Yeah, it's complete. So this completeness of functions is very important, okay, to ensure that our answer will converge to the exact answer, okay. Without this kind of freedom, okay, the solutions later on may not able to converge to the right or the correct exact answer, okay. So this is very important, right? When we start to derive or to select the displacement function for any type of finite element, right? So you can see that exact solutions, okay, the convergence of the exact solutions towards the right answer or the exact solutions would become closer and closer as the number of element increase, okay. So what it means is that in the previous examples, okay, take the previous examples, these examples we use 1, 2 and 3, okay. So therefore what happened is that if there is a force acting, okay, if there is a force acting, okay, or maybe the weight acting, therefore we would expect this kind of characteristics, okay, of displacement later on, right? Okay, so this kind of displacement, there would be an error, okay, as we would expect this with a nice curvature, right, type of deflections, okay. So in order to get the exact or close to the exact value, you have to break it into more elements, okay, break them into the more elements it is, okay, therefore they can form the proper solutions at the end, okay. So this is what is being described by this particular curve, okay. So the convergence of the exact value would be closest when the number of element increase, right? So the last would be just the idea of these approximations displacement functions, where it allows the rigid body displacement. The important is that we would have let's say the nodal displacement for u equals to a1, okay. So this is the first part that allows it to be displaced, right? Okay, so therefore from these equations, okay, we can rewrite it in this form, okay, and this u equals to a1, okay, and we know that a1 should be equals to a2 as well, okay. since the whole rigid body is displaced, okay, the whole object is moving, okay, if this point move certain displacement, then the point number 2 should have the same value, right? So they should be equals to, let's say, a1, right? So we just substitute it into this, okay, u1 u2 is equals to a1. Therefore when we rewrite, okay, resolve it, then we will see that is n1 plus n2 multiplied by a1 equals to u, and eventually, since this is equals to this, right, therefore n1 plus n2 must be equals to 1, and this is the, again, a conditions that must be satisfied, okay, when we so-called derive the shape functions, okay, of the finite element itself, okay. So make sure n1 plus n2, or maybe if later on you deal with more than 2 parameters for the displacement functions, therefore the summations of all of it must be equals to 1. All right, so that's all for today's sessions. We will make it very short, all right, so that you have again time to process, okay, as well as you can start to do some practices in the practice questions given at the end of this slide, right? And also, before we we call this to an end, okay, we will have the second quiz, okay, again very simple, 3 questions, okay, just go and answer it, okay, based on this, okay. So I think the link given in the slide, okay, in the Google Classroom is wrong, okay, but then don't worry about that. You just go to the Google Classroom. There is a quiz tool, right? Use that to enter to the quiz form, right? It's only 3 questions, right? Okay, so in the Google Classroom slide, okay, the link is wrong, okay, but this is correct, right? Okay, so just make sure you take this quiz. Again, the time or the due date would be 4 days, since tomorrow is public holiday, so I give you until Monday, okay, to try it, okay. Very straightforward. I would suggest you to go and answer it immediately, okay, as you are still fresh about what we have discussed previously, right? So that's all from me for today. We will see you again on Monday, right? See you and take care. Bye bye.